this, under this heading, we're going to derive the so-called matched filter. Which is the optimal. Optimal in terms of minimum probability of error detection filter. Okay, in order to simplify this derivation, which gets a little complicated, we're going to make two assumptions. So two simplifying assumptions. First, the input bits are equiprobable. In other words, probability 0 is equal to probability 1, which is 1/2. Second, the waveform S1 of k is equal to a scalar multiple of S0k, and I'll call that scalar alpha. In other words, if I have S0k, S1 of k is just some multiple of that. And we've seen three examples of modulation schemes so far: polar NRZ, BPSK, and on-off keying. And all three of them satisfied this. On-off keying satisfied with alpha equals 0, because we just had a square wave for a 0 and a flat all 0 to transmit a 1. The other two satisfied, so for instance, polar NRZ, what was the value of alpha for that?
Minus.
It'd be -1, that's right. So, and same thing for BPSK. So S0, we multiply by -1 to get signal number 1. It turns out that if this is violated, if you can't express S1 this way, and you're only using one filter, it actually makes no difference. So, because what you can do is you can then express S1 in terms of alpha S0 plus something that's orthogonal to S0 in a vector space sense, and that thing that's orthogonal gets thrown out. So this assumption, although we're going to use it for convenience, is without loss of generality. This assumption implies some loss of generality, but I would have to rederive it, but I'm pretty sure that this doesn't make an impact on the final result. Okay. So we had what we really want to do is we want to talk about S0 and S1. So let's write S0. Remember, S0 is the noise-free filter output on input 0. So S0 is equal to S0k involved with h of k, evaluated at NB, which is equal to the sum over I S0I h of NB minus I. To simplify my notation at this point, I'm going to say let h hat of k be equal to h hat of I be equal to h of NB minus I. change of variables. In practice, what that means is I will shift h. I will shift h by nb and time reverse it, and that becomes hi. So basically, all I'm doing here is I'm rearranging the elements of h. But what that lets me do is it lets me write the following: S0 is now equal to the sum over I of S0I. So basically, substituting directly here, I just have h hat of I. So again, all I'm doing is I'm rearranging the elements in the filter, and then later on, when I want to get the filter impulse response, I'll just rearrange them back. Okay, what's S1? Well, so S0 is this. S1 is the sum over I of S1I, h hat I. What's the relationship between S1 of I and S0 of I? They're scalar multiples, so I can substitute that with alpha sum I, S0I, h hat of I, which is equal to alpha S0. So S0 is equal to this somewhat simplified expression, and S1 is equal to alpha times S0. So let me write these. At the top just for reference. S0 is the sum over I. S0I h hat I. S1 is alpha S0. And what's the third thing we need? Sigma squared, the variance. Variance, sigma squared, is equal to n0 over 2ts. The original expression we had was the sum over I of h of I squared. Now, h hat I is a rearrangement all we're doing with h hat of I is permuting the elements of h of I in some way. So if I'm summing over all of the elements of h of I and squaring them, it doesn't really make a difference in which order I take that sum. So this should be equal to n0 over 2ts, sum over I, h hat of I. That's just because, again, all I'm doing with h hat is I'm rearranging h, so if I'm summing over all of them, it doesn't make a difference if I do that in a different order. So variance is n0 over 2ts, sum over h hat I squared. All right, we know S0, S1, and sigma squared. What's next? Something else we need in order to calculate probability of error. Z, threshold.